The height is 3,700 meters. The weight of individual fragments reaches 200 tons. There is not a drop of binding material between the blocks, but the joints are so tight that a knife blade cannot pass through them. This structure withstood cataclysms that turned more modern buildings in Cusco into ruins. What you see before you is not just a fortification. From the perspective of classical engineering, this wall should have crumbled to dust centuries ago. But it stands. It has survived half a millennium of colonization, dozens of powerful earthquakes, and the colossal pressure of its own mass on a mountain ridge, where the air is thinner than on the peaks of the Rocky Mountains. Official history asks us to believe in 3 ingredients for success: diligent craftsmen, an abundance of free time, and incredible luck. Let's arm ourselves with numbers and see if this theory can withstand a collision with reality. The first critical factor is altitude. Construction at 12,100 feet is not romanticism, but harsh physics. Atmospheric pressure here is only 65% of normal. Copper tools feel heavier, lungs struggle with the load, and ropes behave quite differently in the cold than in the lowlands. If you decide to build here today, you'll need a week to acclimatize before you even look at a 200-ton block. And it is the weight of these blocks that is the second headache for proponents of the classical version. We're not talking about a couple of stones, but entire tiers. The mass of the largest elements at the base of the zigzag wall varies from 90 to 200 tons. The chronicler Garcilaso de la Vega called it the work of giants, and he was not trying to embellish reality. His mind simply refused to find other definitions. It was an admission of technical defeat. Academic science insists the Incas used ramps and crowds of workers. Well, let's calculate. Let's take a 150-ton block. With a friction coefficient of 0.6 against the ground, it requires a force of 900 kilonewtons to move it horizontally. That's approximately 1,500 people pulling ropes. The problem is that there is physically no space around the stone for such a crowd. And keep in mind, we haven't even started the uphill climb yet. A moment of your attention. Official historians love the term communal labor. It sounds noble, but in reality, it's just an attempt to cover up the lack of clear explanations with a beautiful epithet. Just when you think there are enough difficulties, geometry enters the game, silencing engineers. There are no straight lines here. The blocks do not have 4 even faces. These are complex polygons with 6, 8, or 12 sides, each perfectly fitted to its neighbor. Why such complexity? If your goal is simply to build a wall, a right angle would be many times cheaper. All global construction experience screams this. So who and why spent such resources without a compelling reason? And here we find the first clue. Look at the joint up close. 2 multi-ton blocks meet along a curved line. In the center, there's a barely noticeable bend, narrowing towards the edges. This isn't aesthetics, it's peak engineering. Try to slide the thinnest steel plate in there. You won't succeed. Not in the center, nor on the side. The fit is so perfect that water can only penetrate due to capillary action. This is not just a facade. Usually, we are told, the Incas were fantastically patient. But patience has nothing to do with the laws of statics. And the statics of polygonal masonry are fundamentally different from brickwork. A regular block can fall out of a wall. A polygonal one is locked in place. It is held by 2 to 5 neighbors at different angles. This is not a wall, but a gigantic 3D puzzle, where any external load is instantly distributed throughout the entire structure. Want to know why engineers haven't left these stones alone since the 19th century? The answer is simple. They don't understand how it was done. Researcher Jean-Pierre Protzen dedicated decades to this question. He looked at the problem through the eyes of a builder, not an archaeologist. His conclusions are sobering. The precision of the fit is maintained throughout the entire depth of contact. That is, the stones were not just roughly trimmed from the front by eye. They were cut so that they interlocked within the wall for tens of centimeters. This is a volumetric fit, not a linear one. To achieve such a result, you would have to repeatedly lift and lower a 150-ton block for fitting. At an altitude of 3,700 meters, you can call it patience. I'll call it something else. A high-precision technological process requiring at least cranes, reference measuring instruments, and a clear understanding of tolerances. That is, everything that, according to historians, that era did not possess. But if the mystery of the joints seems complex to you, look at the root. How did these stones even get to the top? This is the second part of the equation, and it's even crazier than the first. The quarry for diorite is not at the foot of the mountain, but in Rumicolca, 20 miles from Cusco. 20 miles on a map is nothing until you see the terrain. The path goes through passes and narrow gorges, over viscous soil and sharp rocks. At such an altitude, any pack animal expends more energy on its own survival than on pulling a load. The Incas had no wheels. They only had llamas, capable of carrying a maximum of 25 kilograms, not 150 tons. Calculate it yourself. 150 tons is approximately 6,000 llamas to transport one stone. This woolly river would simply clog all the mountain trails, and that's assuming they carry the load. For dragging, you need people, ropes, and log rollers. But at an altitude of 12,100 feet, trees of the required diameter simply don't grow. It is at this point that the official version begins to crumble. Someone might object. They were just dragged along the ground. Sounds cute, but a 150-ton block dragged 30 kilometers across the Peruvian landscape would leave a furrow visible from orbit. There are no such traces. Instead, we see the construction site itself. At the foot of Sacsayhuamán lie blanks, chips, rejects. This means people worked here on site. But there's a strangeness, a chasm between what lies on the ground and what is built into the wall. Below are ordinary blocks with traces of primitive tools. Above are 150-ton monoliths with mirror-smooth fitting. It feels as if the construction was carried out by two different groups. One possessed future technologies, and the second only tried to imitate them. Let's summarize. We have extreme altitude, impossible logistics, geometry requiring precision tools, and a route impassable for pack transport. 4 factors, each of which is baffling. One stone can be attributed to chance, but only until an earthquake begins. When the earth shakes, ordinary walls crumble. But the polygonal masonry of Sacsayhuamán withstands. Its joints are not just beautiful. They are a shock absorption system where blocks can shift slightly without losing stability. Another lucky coincidence? Or is it the calculation of the creators of this impossible geometry? Peru is located in one of the most unstable regions on the planet. At a rate of about 3 inches per year, the Nazca Plate literally wedges itself under the South American continent. It sounds like a slow and boring process until the accumulated tension is released in an instant. In 1650, a powerful tremor wiped out most of Cusco. In 1746, Lima suffered the same fate. In 1950, the elements struck the center of Cusco again, turning colonial cathedrals, government buildings, and residential areas into ruins. The Spanish heritage suffered critical damage. But above all this chaos stood a wall that was 8 centuries older and remained virtually untouched. What we have here is not just a historical curiosity. It's a global crash test of material, conducted by nature itself over centuries. Here, it's worth recalling the research of ETH Zurich, Swiss Federal Institute of Technology, Zurich. Local specialists have been studying the seismic resistance of buildings for years, particularly the behavior of dry masonry during tremors. Classical European constructions with rigid bonding have only 2 scenarios. Either the structure holds or it cracks. There is no third option. Once the first serious crack appears, the building's statics are compromised. In a prolonged confrontation with an earthquake, such a wall is doomed. No alternatives. However, polygonal dry masonry offers a different approach, the ability to yield. Here, the stones are not bound by mortar. The blocks possess colossal weight, yet they retain a certain freedom, allowing them to shift by fractions of an inch without losing integrity. A seismic wave passing through such a barrier is dampened in the joints due to microscopic movements. The stones seem to perform a dance, and then, under the influence of their own mass and complex geometry, return to their original position. No magic, just the physics of friction, gravity, and precisely calibrated joint angles. And here arises a question to which official history has yet to provide a clear answer. If the wall was designed to absorb seismic energy, who was behind these calculations? Any calculation requires a deep understanding of processes, which is impossible without prolonged observation. Observation, in turn, requires time. But academic science claims that the civilization had less than a century and a half of active construction to erect Sacsayhuamán. In 150 years, one might manage to test a technology in theory, but it's impossible to scale it to the level of 200-ton monoliths, conduct field tests, and perfect the method. It is more logical to assume that this technology is much older. And the Incas acted not as creators of the system, but as its heirs. Let's clarify immediately. We are not looking for traces of aliens. We are talking about perfectly earthly, but forgotten engineers of deep antiquity. Let's call a spade a spade. This structure is a passive seismic damper. Ancient builders achieved with stone and geometry what modern specialists implement through polymer reinforcement, hydraulics, and complex computer modeling. The German Research Center for Geosciences in Potsdam has been recording seismic activity in the Andes for decades. The scientists' verdict is unequivocal. The soil here is in constant and powerful motion. And it is on this unstable ground that the wall stands, looking as if it was specifically optimized for these conditions. We have no direct evidence, but there is a fact. Nature tried to destroy this structure time and again, and each time, the wall won. One could delve into philosophical discussions, but it's better to stick to the facts, especially since there's a detail that makes the engineering task even more puzzling. The Spanish tried to finish what the earthquakes couldn't. They simply decided to dismantle the wall. After the collapse of the Inca state, Sacsayhuamán became a convenient source of building materials. The colonizers removed the upper tiers of masonry to erect Baroque-style buildings in Cusco. Monasteries and palaces in the old city today are adorned with those very stones taken from above. Historians delicately call this secondary use, but in fact it was a systematic dismantling. However, they couldn't dismantle everything. After dealing with the upper rows, the colonizers faltered before the lower blocks weighing 150 and 200 tons. They were stopped not by admiration for ancient art, but by elementary powerlessness. There weren't enough tools, people, or patience to move what the Incas, or their predecessors, had set in place for centuries. European construction thought of the 16th century capitulated before the achievements of a primitive people. And this is not a subjective opinion, but pure mathematics. But the mysteries are not limited to what is above ground. Sacsayhuamán is not just a defensive line. The hill it stands on is literally riddled with voids. Researchers know of at least 4 systems of underground passages and halls, both natural and man-made. The most famous labyrinth, Chincana Grande, was blocked by Peruvian authorities in the 1970s. The reason is simple: people disappeared there without a trace. Despite the efforts of scientists from the University of Tübingen, a complete map of the underground remains elusive to this day. The mountain stubbornly conceals its inner spaces. At this point, the concept of a fortress crumbles. Fortifications have a clear plan and logic of defense. Sacsayhuamán, however, consists of damper walls and a mysterious underground network. Rather, it is a complex infrastructure object with functions extending far beyond military affairs. Perhaps it was a water supply system, warehouses, or, as archaeologists like to say, a ritual complex. Most likely, it was all of these simultaneously. The topic of infrastructure inevitably leads us to water. At an altitude of almost 4,000 meters, water is life. Around the complex, channels are carved into the rocks, stretching for enormous distances. Some of them lead to pools with an overflow system, while others go deep into the mountain, to those very tunnels. The designer of this system didn't just lay stones. He created a hydrogeological complex that has functioned for centuries without pumps or repairs. Specialists from Tübingen have been recording the parameters of these channels for years. The result? The slopes are so precisely calibrated that water does not stagnate or erode the bed. This is the result of meticulous calculations, not blind luck. Another nuance of polygonal masonry that is often overlooked: the joints here are individual. An ordinary craftsman makes typical connections. An engineer, however, adapts the joint to a specific load. In Sacsayhuamán, the geometry of the joint at a corner is fundamentally different from that in the center of a row. Where a seismic impact hits 2 planes at once, the contact surfaces are enlarged, and the bond is made deeper. On straight sections, the connections are simpler. The builder knew the weak points of the structure precisely and reinforced them specifically. Today, professionals call this adaptive connection under load. This is the cutting edge of modern seismic engineering, described in textbooks only in the last 30 years. And finally, the question of time. The official version states that Sacsayhuamán was built under Pachacuti at the end of the 15th century, and the work took about 60 years. 60 years for everything: 200-ton blocks, irrigation, tunnels, and the most complex joint geometry. Simple arithmetic shows that builders would have had to install one giant block every 3 months, and not just transport it, but perfectly fit it to its neighbors, which also needed to be carved. This sounds not like a historical fact, but like an impossible dream. There are other estimates as well. Geologists suggest that the foundation might be 1,000 years older, and some bold researchers cite even more impressive figures. But the main question an engineer asks when looking at these walls is, how many centuries did it take to develop such technology? And the obvious answer is that it took much longer than the lifespan of a single dynasty. The main question of our investigation gains extreme clarity here. If this is not an ordinary fortification, then what is it really? Let's compare all the available data. We have 5 key arguments that we analyzed one by one, and now we'll evaluate them as a whole. Point number 1. The 12,000-foot altitude, which turns construction into a living hell for any engineer due to the laws of physics. Point 2. 200-ton megaliths that had to be dragged 22 miles across terrain impassable for pack animals. The third point, polygonal masonry with 3D joint precision, impossible to achieve without multiple attempts to fit these giant blocks. Fourth, earthquake resistance, which our contemporaries can only calculate with powerful computers. And finally, fifth, a network of underground communications, the full map of which is still missing. Each of these facts individually causes bewilderment, but collected together, they transform from a set of oddities into a unified system. To call such a structure simply a fortress means going against logic. Instead of ordinary masonry, we see a complex apparatus. This is a passive engineering device designed to capture destructive energy and transform it into thermal radiation. It has no familiar levers or gears. Movement is present here, but it is so microscopic that the human eye does not detect it. And this machine has been functioning properly for over 6 centuries, and possibly longer, without requiring repair. Try to find even one modern object with a similar resource. At this point, we inevitably move into the realm of philosophy, just for a moment. The term primitive has firmly entered our lexicon without any verification. We use it simply because colonial officials decided so back in the 16th century. It was easier for them that way, and we got used to it. But if a people can move 200-ton stones at dizzying heights, if their buildings stand where Spanish temples crumble, and if they designed labyrinths that we are unable to fully explore, what definition would be more accurate? Were they primitive? Or did they possess knowledge of which we have no idea? So we've come full circle and returned to the starting point. First, we just looked at the wall. Blocks weighing 200 tons, 12,000 feet high. Not a gram of cement, not a single gap where a knife blade could fit. It simply stood before us, silent, heavy, and incomprehensible. That was the first glance. Now we look at the same object, but we see something different. The wall no longer seems static, it is in action. Every element here is a part of a system whose essence we are only trying to grasp. This structure lives. It is a device that calculates every tremor of the soil and dampens any vibrations second by second. And when the question arises about the creators of this marvel, we can only acknowledge the obvious. We have no answer. And the wall continues to stand.